In this lecture, before starting to talk about particular sets of constraints or their separation problems, we should first clarify what we mean by a strong constraint. We've seen the Shaftal-Gomery cuts, and we saw that all valid inequalities are some Shaftal-Gomery cut. Remember though that there's quite a lot of them, and a lot of these cuts actually don't have any purpose at all. For example, this cut is a pretty useless cut. However, knowing that any valid inequality can be written as one of these type of inequalities tells us that these inequalities are very powerful. What we'd like to look for, though, is some weaker sense in which a set of constraints or a set of cuts can be strong without including every possible cut. Intuitively, the cuts that we'd like are the cuts that define the faces of the convex hull of X. Recall that the convex hull of X is the set of all points that can be written as a convex combination of the points in X. Here I've drawn the convex hull of X. A constraint defines a face of the convex hull if it happens to be identical to it. In this case, both of these constraints intersect exactly with one of the faces of the convex hull of X. The constraints we don't care about are the constraints that don't define faces. For example, this constraint doesn't even intersect with the convex hull of X, and so we don't really care about it. Alternatively, a constraint that only hits a particular point of the convex hull of X, although it can be valid, if it doesn't define a face, we also don't care about it. In some sense, it's redundant because we can have two other constraints, say this constraint and this constraint, that are strictly better than it. We're going to make all these ideas more formal. What we would like is a formal definition of a face, and in particular, the face of the convex hull of X. To do that, we first need to explore dimension in affine independence. The affine independence relationship is a relationship between a set of points inside of a space. We say that x1 through xk is affine independent if the vectors defined by x2 minus x1 through xk minus x1 are all linearly independent. This is equivalent to saying that the vectors x1 appended with the entry 1 through the vector xn appended with the entry 1 are all linearly independent. In this case, we're looking at vectors inside of the space that has n dimensions, and in this case, we're looking at vectors that are inside of an n plus 1 dimensional space. Either one of these definitions suffices. Here we have a set of points, and we can see exactly what points are and aren't affinely independent. In this case, if we look at the points x1, x2, and x3, they're all affinely independent. There is no line that defines them. However, if we look at the points x1, x3, and x4, all of these points lie on the same line, and so they aren't affinely independent. We can check that these respective sets are and aren't affinely independent by going back to our particular definition. We'll use the first condition. If we look at the vector x1, x2, and also at the vector x1, x3, we see that these two vectors are linearly independent. We can't write one as a linear combination or a multiple of the other. However, if we look at the points x1, x3, and x4, and we look at the vector x1, x4, and the vector x1, x3, we see that x4, or the vector x1, or x4 minus x1, is just a linear multiple of the vector x3 minus x1, and so these points aren't affinely independent. Affine independence allows us to define dimension, and in particular, it allows us to define the dimension of a polyhedron P. The dimension of a polyhedron P is one less than the number of points that are affinely independent inside of P. In our example, we found that there's at least 3 points that are affinely independent: x1, x2, and x3. And so the polyhedron that encloses these 3 points has dimension equal to 2, one less than the number of affinely independent points. It's easy to see that we can't find 4 points inside of P that are affinely independent. And so the dimension of P has to be equal to 2. Now that we've defined affine independence and dimension, we can start talking about faces, and in particular the faces of the convex Hall of X. Over here we have pictured a set of feasible points X, and we've outlined the convex Hall of X. We're going to define faces with respect to a polyhedron P. Our interest is generally going to be in the convex Hall of X, but our definitions are going to hold for any polyhedron P. A face of a polyhedron is a set of points F, defined with respect to a polyhedron P, and F includes all the points in P that satisfy some equality. This equality has to be some valid constraint for P, where we change the equality to a constraint by taking the less than or equal to version. There's 2 things to note about this definition of face. First, a face is defined with respect to a particular equality. This is the defining equality of the face. Second, a face, to be non-empty, has to only include exactly 1 point of the polyhedron P. So, for example, if we have a constraint that meets our polyhedron P at exactly 1 point, like this red constraint, it defines a face of P. This is despite the fact that it violates our intuition about what a face should be, because it has exactly 1 point in it. So really, what we'd like to do is define what we intuitively mean by a face. What we intuitively mean by a face is going to be called a facet. F is going to be a facet of P if F is a face of P, and the dimension of F is equal to the dimension of P minus 1. In this way, a facet of P is a hyperplane that sort of defines our original polyhedron P. In our graphic, the 2 green equalities define faces of P, but they also define facets of P. Whenever we talk about faces and facets, we're strictly speaking talking about a set of points. But usually what we're going to do is instead talk about the equality that defines the face or facet. Now that we know what faces and facets are, we can go back to our original intuition and sort of update our notation. The cuts that we're going to care about aren't defined by faces of the convex Hall of X, but they're defined by the facets. If a constraint defines a facet of the convex Hall of X, then it's intuitively a constraint that we care about. So far, our idea about why these are the constraints we care about, the facet defining ones, is just an intuitive idea. We'd like the constraints that give us the most information. We can see exactly why the constraints that define facets give us the most information. If we have a facet, and a particular constraint that defines this facet, then this constraint is necessary to define our polyhedron P. And this constraint is going to be necessary if and only if it defines a facet. We could potentially prove this, but we're not going to go into the proof details. We just like an intuitive idea. The intuitions go something like this. Here we have a particular graphic with a polyhedron P. We've extended 2 of the constraints that define this polyhedron P just for visualization purposes. In addition to the constraints that define P, we also have another constraint that defines a face of P, not necessarily a facet. We can see that it intersects P at only 1 point. Now we ask ourselves the question, what happens if we remove one of these constraints that defines a facet of P? Let's suppose we remove this constraint. The result is that we end up defining a new polyhedron, P. We get these additional points shaded in blue. Because of this, these facet-defining inequalities are sort of the inequalities that are necessary to define our polyhedra. If we get rid of one of our facet-defining inequalities, or one of our facets, then we have a new polyhedron. So now we can go back to our original question and ask ourselves, what defines a strong cut without including all of the cuts? The answer is that a set of cuts is going to be a set of strong cuts if the inequalities defined by these cuts define facets of the convex Hall of X. This is going to be our benchmark for the strongest set of cuts. If we recall our Chavatal-Gomory cuts, these defined all of the valid inequalities. And so, necessarily, the facet-defining inequalities are going to be inside of this set. What we're going to be doing in the rest of this lecture, though, is going to be finding smaller sets of cuts. Sets of cuts where not all valid inequalities can be expressed as one of these cuts, but only the facet-defining ones can be expressed as these cuts. After we find these set of cuts, we're also going to find the corresponding separation problem. This is going to allow us to use these cuts inside of a cutting plane type algorithm.